So we continue with the previous lecture on stable system, unstable system, and marginally stable system. Right. So here this picture shows the S-plane representation and the time response characteristics. Right. So for various values of zeta, from zeta equals 0 to 0 to 1. Zeta is the damping ratio. So in underdamped system, the zeta value is between 0 to 1. For undamped system, when there is no damping is there, then zeta is 0. For critically damped, zeta equals 1. Then over damped system, zeta is greater than 1. Right. So look into this picture. In this picture, so here, this is a stable system, a representation of a stable system. In the beginning, when time t equals 0, the system is unstable. After the damping is implemented, the controller brings the system to stable state. Right. Then the second one is it's a neutral system. Okay. So there is no damping is needed because the system is already it is unstable and it oscillates within the limits. Okay, so this is a neutral system. Second one, last one, this one is undamped system. Okay, so when T increases, the system deviates from stability and keeps on the oscillations is increasing. So this is undamped system. Then stability. So what is asymptotic stability, absolute stability, relative stability? We look on it. So bounded input and bounded output. Output must be bounded for a bounded input. Okay. The output also should be bounded within the limits. So asymptotic stability. What is asymptotic stability? If system input is removed from the system, then the output of the system is reduced to 0. If the input is removed, the output should be 0. This is asymptotic stability. Usually we can observe asymptotic stability in some systems. Even though if you remove the input, still it is giving output due to its residual energy inside. So this is asymptotic stability and instability. Right. Next one is absolute stability. So what is that absolute stability? One second. What is that absolute stability? A system is stable for all values of the system parameters for bounded output. So for bounded input, the system should be stable. Okay. So this is absolute stability. Based on the location of force, the stability is determined. The next one, these can be calculated using Routh-Hurwitz criterion, root locus, and an IQS plot. Next one is a relative stability. So this is a quantity measure of how fast a system oscillation die out with the time and how fast steady state output reached. The relative stability, how fast the system behaves for oscillations. So this is relative stability. This is defined in the terms of damping ratio, gain margin, and phase margin. This stability can be determined using Bode plot and polar plot. System having poles away from the imaginary axis of S-plane in negative direction have higher stability. Okay, in S-plane, if the poles are on the negative side of the S-plane, the system is stable. On the right side, and then on the positive side of S-plane, then the system is unstable. Okay, if based on the roots, we can determine the stability. Right. What is my conclusion? For a stable system, all the roots of the characteristic equations, that is poles of the system, must lie on the negative half of the S-plane. On the negative half of the S-plane, with real negative part, with the negative real part and imaginary components. Right. If the roots lie on the imaginary axis, system is called marginally stable or limitedly stable. Okay. If the roots lie on the positive half of the plane, the system is unstable. Right. If there are repeated poles or roots on the imaginary axis, then also the system is unstable. Repeated poles and roots on the roots. If there are repeated poles or roots on the imaginary axis, if it lies on the imaginary axis, the system is unstable, right? The poles move away from the imaginary axis towards left side of the S-plane, then the relative stability of the system is improving. If the pole starts moving from the imaginary axis, then the system is stable. Right. So this is my conclusion. Look into this picture: unstable system and stable system. So here this is the overall view of a unstable and asymptotically stable system. At least one of the system pole is in the right half of the S-plane unstable system. All the system poles are inside the left half of the S-plane asymptotically stable. So stable. Then at least some of the system poles are repeated and it is unstable. All the poles on the imaginary axis are simple and none of the poles are present in the input. Poles on the imaginary axis are simple and none of these poles are present in the input marginally stable. At least one of the system poles on the imaginary axis is present in the form of a pole, exhibits instability due to resonance. Okay. The left side is stable, right side unstable. If it is on the imaginary axis, it is marginally stable. Right. So thanks for watching. We continue this in the next class.